in this video we will be discussing about diagonal sum approach. So in the last video we have discussed about how can you calculate the sum of the diagonals of any 2D array matrix, right? But what was the problem there? Their time complexity was O of n square. But in this video we will be showing you like how can you optimize the diagonal sum problem from O of n square to O of n. Have you thought about it, like diagonal sum can be reduced to that much time complexity? Yes, it's possible. Let me show you how. So basically what we did for calculating the diagonal sum, we need to take n cross n matrix, right? So we will be taking n cross n. So basically I am taking here 3 cross 3 matrix. Okay, so here I am taking 1, 2, 3, 4, 5, 6, 7, 8, 0. Let's suppose I am taking this matrix, okay, and I need to calculate the sum of the diagonals. So what will be my sum of the diagonals here? So it's like 6 plus 15. 7 plus 3, 10 plus 5, 15. So how much will be my total? It's 21. So this will be my sum of the diagonal. So now how can you calculate it through optimized approach? The normal brute force approach was we need to make use of 2 for loops. One for loop will go for row, okay, and second for loop will go for column. So for row and column, 2 separate for loops, like nested for loop we have to take, and we need to check condition like if I equal to j and or one more condition we need to check for right diagonal. So there are 2 diagonal, left and right. Okay, so for left diagonal it will be like I and j both will be same. So here it will be like 0 0, here it will be 1 1, here it will be 2 2. Okay, so here you can see I equal to j for primary diagonal, which is left diagonal, and for right diagonal what we have to do, one pattern we have observed, right? So for this what was there, it is 0 comma 2, it is 1 comma 1, this is 2 comma 0. Okay, so there is one pattern, it is 3 cross 3 matrix, and here it's we can see 0 plus 2, 1 plus 1 is 2, 2 plus 0 is 2. That means the sum of row and column will always be less than matrix dot length minus 1. So that we can put it in this if condition here. We can put if I plus j, okay, is equal to this matrix dot length minus 1. Okay, if these two condition gets, if one of these two condition gets satisfied, what we will do, we will make use of sum. Okay, we have defined int sum equal to 0 outside the 2 for loops, and then we used to do, after putting this if condition, we can write sum equal to sum plus matrix of I and j. Like this we can calculate the sum of the diagonals. Okay, so this was my approach for brute force, but there was time complexity of O of n square because of nested for loops here. There were 2 for loops, one is going from I and one is going for j, that is one is for row and second is for column. But can we optimize it, like can we remove one of the for loops? Yes, it's possible, but for that we need to understand the function concept. Okay, so how can we understand the function concept? So here you can see like I plus j equal to matrix dot length minus 1. Here you are making use of j. Okay, so can we optimize it, like can we remove j from here? Is it possible? So when left equal to right, then I is always equal to j. Then why to take j there? It's not required. We can directly set matrix of I and I. Okay, so we can put like sum plus equal to matrix of I and I. Okay, so that we can make use of for calculating the primary diagonal sum, that is left diagonal sum. And for right diagonal sum, what we can do, the same thing we can approach here, same thing we can do. This is I am doing for optimized approach, I am doing it here. Okay, so here what you can do like sum plus equal to matrix of I, and instead of j what you can write. So what was the condition which was being satisfied here? I plus j equal to matrix dot length minus 1. So what will be my value of j from here? The value of j will be matrix dot length minus 1 minus I. You got it right? Simple. It's like moving the variable I to the right hand side. So value of j will be substituted with matrix dot length minus 1 minus I. That means j has been calculated as a function of matrix length and I. Okay, it's very simple. So instead of j we can write matrix dot length minus 1 minus I. So here you can take like minus I minus 1 or minus 1 minus I, both ways it's possible. So I am taking length minus 1 minus I for better understanding. So here you can do it here, okay, but can you think it of here? There is one problem here. What one problem can you face here? That one problem is that intersecting point. For if it is of even numbered m cross m matrix, which where m is even, so in that scenario there will be no intersecting point, there will be no overlapping point of the two diagonals. But for odd numbered n cross n matrix, you will always find that there will be one intersecting point in the two diagonals. So if you don't write any condition, if you directly as it is put these two values for calculating sum, then what will happen? 5 will be added 2 times, like 1 plus 5 plus 0 plus 3 plus 5 plus 7. It will give me wrong answer because 5 is added 2 times. Now how can we put that? How can we remove that condition here? Then we need to put one condition, because this is the right diagonal, right? So in left diagonal already it is being added. So in the right diagonal sum calculation we will not put that 5 again. So for that we will put a condition here. So we will put the condition like if I is not equal to n minus 1 minus I, where n is the matrix dot length. Okay, so first saving some space I am putting directly n. So n you can understand like it's matrix dot length. So you can put like if I, which is the row part, is not equal to matrix dot length minus 1 minus I. Okay, so if it is not equal to this, then only we will write this. So why I am putting n minus 1 minus I? So length of the matrix is 3, 3 minus 1 is 2. Okay, so if it is coming at this particular point is 2 minus 1 will be 1. So if I is 1 and here it is 1, then it will be 1 comma 1. Okay, and 1 comma 1 is this point, which is already been calculated above for primary diagonal sum calculation. So this should not be added again. So for that we are putting this condition. This is very important condition for optimizing the two diagonal sum approach. So if I is not equal to n minus 1 minus I, that means we are omitting this intersecting point of two diagonals, then we will do the sum. Now it will give proper output. So now if after putting this condition you will check and write the code by yourself, and then you will do dry run, or you can run it on the compiler. You will see like 5 is not being added and you will get the output as 21. And if you don't put this condition I not equal to n minus 1 minus I, output will be 26. Okay, so you can try it out, you can check it out in your compiler, you will get the output. So I hope you got the concept, and it's very much important. It can be asked in the interview like how can you optimize this diagonal sum concept. So if you look at an overview concept, it will be very much easy. Okay, there is nothing much in this. But if the interviewer tells you like, can you reduce its time complexity, then you will be thinking like, how can you reduce one of the for loops. So this algorithm is very much important. So try to do it by yourself and do dry run and try to practice it a lot. You will get the concept. And any coding problem you are doing, think of it like, can I reduce its time complexity a bit? It's not like you have solved your problem with any time complexity, that means your task is done. No. Try to reduce its time complexity to the minimum possible. If it is possible. In some scenarios, it will not be possible to reduce the time complexity. For example, if you see bubble sort, selection sort, insertion sort, those all are having O of n square. You can't reduce its time complexity. That's why merge and quick sort came. So that also analysis you have to do, whether it's possible to reduce or not. And if it's possible, then you have to go for the optimized approach, because interviewer will look for optimized approach solution. So I hope you have understood the concept, understand the approach towards the problem. Okay, so we'll see you in the next lecture in the next set of problem statements. Till then, bye bye.